Hi everyone, welcome to week 9 of incomplete data analysis, and this will be a light week where we will be learning about the package mice for performing multivariate imputation. So let us start. As we have seen last week, there are several packages in R for performing multiple imputation. They basically differ in the method or in the approach they implement in step 1, because then step 2 and step 3. Step 2 is our analysis of interest, and step 3 is combining the results using Rubin rules. But in step 1 is where most of the packages differ in the approach they implement, and we will be studying in detail the package mice, which stands for multiple imputation by chained equations. And to start, we will be assuming that we only have one variable with missing values, so univariate missingness, and for now we will also assume that the variable that has missing values is continuous. Later in this week we will be looking, or in this presentation more precisely, we will be looking at the case where the variable with missing values does not need to be continuous. It can be a binary variable or a categorical one. And next week, and to conclude our course, we will be looking at the case where several variables have missing values. So multivariate missingness, which is the most realistic situation in practice, and also where mice Chinese. But let us start. This is a scheme that we have already seen several times, but now the difference is that we have here the functions that mice has to implement each of the steps. So we will be using the function mice to do step 1. To do our analysis of interest, it's the function with, and to pull or combine the results from step 2, we use the function pull. We will be then doing a practical session in R where we play with these functions. But right now what I want is to give you an idea of the methods that mice implement for step 1. Okay, and this is the image from the paper published in Journal of Statistical Software describing the mice package, and the authors are the authors of the package, Van Buren and Grotius. I have no idea how to pronounce this, but we have the paper describing the mice package on Learn. I have uploaded the paper to Learn. Okay. So, as we have just seen, mice has 3 key functions, and each of these functions corresponds to the steps that we have in multiple imputation. So mice is for step 1, with is for step 2, and pull is for step 3. But as I said, we will be having a practical session, so no need to delve in the details right now. So we will start devoting our attention to the function mice, not to the function mice, but to the methods that are implemented or available to us in the function mice for step 1. And this can be the methods that we want to use, or the methods that are implemented. We have a function, an argument in the function, which is the argument method. And because we are assuming our variable is continuous, and under the assumption that it follows a normal distribution, we will see later extensions of this, there are 3 methods available. So norm.knob implements stochastic normal linear regression imputation. So it's just stochastic regression imputation conducted m times, and m it's the number of copies of the data set that we have made. And as we have seen last week, this approach is known in the literature as improper multiple imputation, because what we do is we fit our regression model to the complete cases, and then we predict the missing values using the coefficients from the fitted regression models in the complete cases, but we are using the same regression coefficients for all copies of the data set that we have made. So we are ignoring that we have uncertainty about these estimates. And this leads, as we also have seen, to overconfidence, or in other words, to confidence intervals that are too narrow or too short, and obviously these have implications in terms of the coverage of the intervals. We usually have a slightly under coverage. And then we have the method norm and norm.boot, where they also do they also implement linear regression model. They add noise, so it's the same as stochastic regression imputation, but we are using different parameters or slightly different estimates for each of the copies of the data set that we have made. And norm, it draws the parameters for each copy of the dataset that we have made from their posterior distribution. And norm.boot, it's kind of the frequentist counterpart. So what we do is, for each copy of the dataset that we have made, we take a bootstrap sample from our complete cases, we estimate our regression coefficients, and we predict the missing values and add the noise using the parameters from that bootstrap sample. And we take as many bootstrap samples as copies of the dataset that we have made. And so the parameters that we are using, the betas, the regression coefficients, and the estimated variance of the residual term, they are slightly different from dataset to dataset. And also, I think I should mention it also as method, the method equal to mean, it performs mean imputation, and the method equal to norm dot predict, it performs regression imputation. But going back to week 3 and week 4, we know that there is very little to recommend about mean imputation and regression imputation. Well, mean imputation is, we have seen, possibly the worst method to handle missing values. And regression imputation, just by doing regression imputation, we see that we also have some problems. We lack variability, imputed values lack variability, the correlations are artificial increase. So we also have several problems. It is not as bad as mean imputation, but it's not good. And so in fact, stochastic regression imputation and the versions that take parameter uncertainty into account are kind of improvements of regression imputation. But more than that, mean imputation and regression imputation, they do not make a lot of sense, or they do not make sense at all in multiple imputation. And why? Well, mean imputation, we are just imputing the missing values with the mean. So all copies of the data set, they will be the same, right? So analyzing m data sets with m greater than 1, it's exactly the same of analyzing a single data set, because the imputed values, they are all the same for all the copies of the data set. And exactly the same applies to regression imputation, because we also estimate our parameters and then we predict the missing values. There is no noise, that we are not acknowledging parameter uncertainty. So again, the missing values will be the same for all copies of the data set. So we should not really use it. First, because they are not good imputation methods, and second, because they do not really make sense in the context of multiple imputation. And Okay, so let me elaborate just a little bit about the methods that mice implement under the normal linear regression model. So norm.knob, norm, and norm.boot. Just to look at the imputed value. So we have, then there are, of course, the values in the details and how we come up with the estimates. This is a software that it's kind of, it's fast and it's not a black box, but there are a lot of details behind these functions. But let us at least have an idea of what the package is doing. So let me introduce some notation. Let y stand for the variable that has missing values and x is for the fully observed variable. So, and we will be assuming that y given axis is missing at random. So the methods that we are using in mice, they need to assume missing at random. And let us denote by axis observed, this quantity here, the subset of our dataset composed by m rows for which y is observed. So we are assuming that the first m values of y are observed and the last n minus m values are missing. And then let axis missing be the subset of n minus m rows of the fully observed variables for which y is missing, and we denote by y observed the vector composed by the m observed values in y, and by y at missing the vector of n minus m imputed values. Okay, so it's the part that is missing and that we impute using our method. And okay, uh, it here it should be, sorry, it's here norm. I will correct it. It's norm dot knob that implements stochastic regression imputation without acknowledging parameter uncertainty. Okay, so we know that our imputed values, so we have created m capital copies of the data set, and for the m lowercase copy of our data set, the corresponding imputed values are given by this expression, and this is not a new to us, right? So we obtain beta 0 at and beta 1 at from fitting linear regression, a normal linear regression model to the complete cases, and then we add some noise, and this noise follows a normal distribution with zero mean, and the variance is the estimated residual variance. And as we have learned last week, and as I've just mentioned, we are using this beta 0 hat and beta 1 hat and the estimated residual variance. They are the same for all copies of the data set, so they don't have an index m, right? And again, this is known as improper multiple imputation, and it has some problems regarding the coverage of the confidence intervals, or the yes, the coverage of the confidence intervals and the width of the confidence intervals. They are too short. And we have just seen that norm and norm.boot, they overcome this problem, because for each copy of the dataset, they use slightly different estimates of the regression coefficients and of the residual variance. And we have here the expression of the imputed values, and this is exactly the same expression that we had in the previous slide, but now the difference is that the estimates of the regression coefficients and of the residual variance, they are indexed by M. And under norm, the function norm, it performs Bayesian normal linear regression. And so beta 0, beta 1, and sigma, they are draws of the posterior distribution of the parameters, this quantity here. And this is the posterior distribution of the parameters conditional on the observed or on the complete cases. So it's based on the complete cases that we fit our regression model, or that in this case that we come up with our posterior distribution. And as I said a few seconds or minutes ago, the evil is in the details. And for those doing Bayesian theory, we know that the posterior is proportional to the likelihood times the prior, and in mice they use non-informative prior, so there is no way that we can specify prior information that is taken into account into the estimation. But in this case, I think it causes no harm, because there is a lot of things already going on. If we are allowed to introduce also prior information, then things would become kind of complicated. So it has a kind of an algorithm. It's not exactly Jeffrey's prior for those doing Bayesian theory, but it's kind of a Jeffrey's prior. But okay, the main point is that beta 0, beta 1, and the residual variance, they are slightly different for each copy of the data set that we are imputing. So our imputed values, so they are different from data set, from one data set to another data set, not only because we are adding the noise, right, but also because these regression coefficients and the residual variance, they are slightly different. And similarly, norm dot boot does exactly the same, but rather than using the posterior distribution of the parameters, what we do is to the we use the complete cases. We draw a bootstrap sample, and we estimate our regression model based on that bootstrap sample for, say, the first imputed data set. And then we use this equation here. Then we go to our complete cases, we draw another bootstrap sample, we estimate again our regression model based on this new bootstrap sample, and we impute again, and we do this as many times as copies of the data set that we have made. They are both a valid approach in the sense that they perform proper multiple imputation, and they acknowledge parameter uncertainty. Okay. And okay, this is our, we are assuming that our variable that has missing values is continuous. But what about if the, and we have been using normal linear regression models, fits to the complete cases. And what about if the normal distribution is not a good fit to the complete cases? And this is something that it's not too uncommon, I would say. In practice, the data can be skewed, we can have heavy tails by model distributions, and these are only some deviations that we can have from the normal assumption. And Van Buren, he says in his book, The Flexible Imputation of Missing Data, that the effect of non-normality is general small for measures that rely on the center of the distribution, for instance, like means. But it can be substantial for estimates of variance or quantiles. So what can we do? Well, there are several approaches. First, we can transform our data before imputation, and then after imputation, we can back transform our data. For instance, we know that sometimes if the response is positive, we can try to take logs. It's usually our first attempt to try to normalize variables that are continuous and non-negative. And more generally, we could also try the so-called box-Cox transformation, for which the log is a particular case, and see whether this brings data closer to the normality assumption. It may help, it may bring, sometimes a simple transformation is all that is needed, but it's not always possible to find a transformation that makes the data not exactly normally distributed, but close to being normally distributed. And there have been attempts to propose imputation under different distributions or other distributions than the normal. For instance, Liu in 1995 he proposed drawing imputations under the T distribution. The tree is also symmetric. The T distribution is also symmetric as the normal, but it has heavier tails. Heavier tails, it means that we are assigning higher mass in the tail. So for instance, it depends, the T depends on the degrees of freedom, right? So for instance, this can be, for instance, like the normal, and the T can be something like, for instance, like this. By heavier tails, we mean that we are assigning um, higher mass to the tails. For instance, if we have like outliers or extreme values, the T distribution is usually um, a good distribution, or a reasonable distribution to deal with data that has some outliers. And over the years, other authors have proposed drawing imputations from different distributions. For instance, in 2006, these two authors here, they used the Tukey GH distribution, which can take many different shapes. So it does not assume that the shape of the distribution that we are fitting to the complete cases is symmetric as the normal or the T distribution assumes. So we also have the skew normal and the skew T distributions, but I don't think they have been used for creating imputations. And recently there is this package, impute robust, that was uploaded to Quran in 2017, that implements various mice methods for continuous distributions, and in particular they implement the T distribution. So this was not in the screenshot that I used last week of the package available for multiple imputation in Quran. So this one was missing. And there are also a few others missing that I will mention next week in case they are useful for you in the future. But okay, just to make the point, some of the methods in mice, they assume that the variable that we are imputing follows a normal distribution. If this is not the case, or we try to transform before imputation and then after imputing we back transform the data to the original scale, or we use one of these packages, for instance, the impute robust, that they implement mice methods but have other distributions, or the default in mice, and as we are all familiar now, is predictive min matching. And predictive min matching, sorry, and it's the method PMM in mice. It's the default in mice for continuous variables, and this is a semi-parametric approach to imputation, and it's specially useful for settings where the normal distribution is not for data where the normal distribution is not a good fit. If the data, if we look at the histogram of the complete cases, and if we deem the normal distribution to be reasonable, then we should use norm.boot or norm, because they will be the most efficient ones. But in case we have some deviations, or if we want to be on the safe side, then we can or we should use predictive mean matching. And the main idea behind predictive mean matching is to find the cases in our observed data that are similar to the cases with missing values, and then we impute the missing values with an observed with the observed value from one of these similar cases in our observed data. And in order to find similar cases, we use the predicted means, hence the name, predictive mean matching, from a normal linear regression model fitting that we use to the. So basically what we do is we use a normal linear regression model to our complete cases. Then we predict the mean not only of the cases with missing values, but also of those with observed values. And we compare for each missing value, I compare its predicted mean to the predicted means of the observed cases, and then I come up with some metric, and I find the one that it's deemed as a possible uh, donor or similar, and then I use the observed value. Not this was one of the common mistakes that some of you made in the assignment. We use the observed value of the donor, not its predicted value, right? The predicted value is just to find similar cases. Then we use the observed value. This is a hot deck type of procedure, and in hot deck we use the observed values of the donors. But okay, let's look in more detail about predictive mean matching. So basically we define as y at observed the predicted values for those with observed y values, and we denote by y at miss the predicted values for those with missing values in the y variable. And there are various ways to select the donor for case J, right? For each J from, I know that I have n minus m missing value. So for each J in from m plus 1 up to n, I want to find the corresponding donor in the observed cases, right? So I go one by one and I look at my observed cases and I find the donor, and then I use the observed value of the donor, not the predicted value. And there are several ways that we can use to select the donor for case J. One approach is to the donor to be the observed case I. So I is varying from 1 up to m, is the cases with observed y values, is the one with the smallest absolute difference between from all predicted means from the observed cases, is the one with the smallest difference. And this is what we have implemented in the assignment. Okay, and another approach is, okay, I look at this absolute difference, and I form a pool of donors formed by those with the smallest possible difference, and I'm saying that I want d, say, of those. So I compute this absolute difference for case J. So J here is fixed. Then I compute this difference for all I, and then I pick as possible. I pick up as possible donors the cases I that have the smallest or a small difference. The D, sorry, kind of messing up things. So I, for case J, I do the corresponding I look at the absolute difference for all observed cases, and then I say, okay, I want as possible donors the ones that the five that give me the small absolute value difference. So I pick up the five that has, for which this difference is the smallest in our data set. And then from this, say, five, or in the most general case, the possible donors, I select one at random. Okay. And so the approach that we have seen in one and in the assignment is just a particular case of two, in the case where d is set to be equal to 1. Okay, and another approach is to say that the pool of donor candidate is formed by all cases I for which the absolute difference is smaller than some threshold, say eta, and we fixed eta in advance. Okay, and then again we have several possible donors and we select one at random. And The default in mice is option 2. I'm not sure whether option 3 is implemented. And of course, as I've just said, option 1 is implemented because it's a particular case of 2 when d is equal to 1. But option 2, so forming the absolute differences and then selecting the d with the smallest absolute difference and then picking one of them in a random fashion is what mice does by default, and we can control d. There is also an argument to say how many donors we want for our pool of candidates. And uh, also for D, the default in mice is 5. So we have a pool of 5 donors and then we select one of them at random. And again, here are studies for all tastes. Basically, D equal to 1 is generally considered to be too low, and we incur in the risk of selecting the same donor over and over again. And by doing this, we are underestimating the uncertainty about our missing values because we are always imputing like the value from the same donor. But on the other hand, if we let d to be too large, we might pick up one that is in our pool of donors, because basically we are saying that almost every observed case can be in our pool of donors, and this can lead to bad matches. And according to a study made by Tim Morris and some other co-authors in 2015, they concluded that values between 3 and 10 provide the best results in most cases. But also, this also depends on the size of our sample size. If our sample size is kind of reduced, 10 might be too large. And in fact, there was a study made in 2000, published in 2016 or 2017. I do not have the reference here, but they concluded that d equal to 1 was the best option for small data sets. Again, as I said, there are studies for all tastes. Mice by default as d equal to 5, we can just if the procedure that we are implementing in step 2 is not too expensive from a computational point of view, maybe we can rerun our analysis by slightly varying d and see if our results change by a large extent, and if they do, maybe we need to rethink what we should do. But I think D very large or D very low are generally not a good idea. And uh, further point, right? We are computing our predicted means, right, for the observed cases and for the missing cases, and then we do the absolute difference, and we have seen several ways of selecting the donor, but we also need to take parameter uncertainty into account, right? We are matching the predicted means in the observed and in the missing cases, but they are based on estimates of the regression coefficients. And there are several types of matching or ways to estimate the parameters, and type 0. So basically we estimate beta 0 and beta 1 both for predicting the observed and the missing cases by least squares or maximum likelihood from the complete cases. And this is exactly what we have implemented in the assignment, right? We have, from our complete cases, we have fitted the model using LM. LM does least squares. And then we have used the regression coefficients to predict the mean for the observed and for the missing cases, right? So we have used type 0, but this kind of ignores also that we have uncertainty in our parameters. So type 1, what it does is for the observed for predicting the means for the observed cases, we use the regression coefficients based on our complete cases by using maximum likelihood or least squares. And then for predicting the means of the missing values, we use draws from the posterior distribution or estimates based on a bootstrap sample, because again, in the assignment, it was in the context of single imputation, but here we are in the context of multiple imputation, correct? So we have several copies of our data set. So basically type 1 is for all copies of the data set to predict the mean of the observed cases. I use the same estimates from my complete cases. And then to predict the means of those with missing values, I use random draws from the posterior distribution. So my parameters are different from one imputed data set to another imputed data set, or I use the corresponding frequentist, say, counterpart based on resampling the complete cases and re-estimating the parameters. And type 1 is the default in mice, and then type 2, it's to do exactly what we are doing for the missing values in type 1, but both for predicting the means of the observed cases and the missing cases. So basically what we do is we do random draws to predict both means. It has some problems because because then we are doing the difference and kind of the stochasticity, the randomness, say, of the parameters. There is a kind of very technical argument that it cancels out, and that's why the type 1 approach is the default in mice. Type 0 is also available, and it's curious that type 1 was already proposed in Little's paper in 1988, where predictive mean matching was proposed, and it was kind of ignored for many years. And it was not until like 2010 or so that some studies have shown that in fact it's kind of the best way to acknowledge parameter uncertainty, and that's why it is the default in mice. So default in mice is type 1. For predicting the means of the observed cases, we use the estimates based on our observed data, and then to predict the means of those with missing values, we use random draws from the posterior, or we re-estimate the parameters from based on bootstrap samples of the observed data. To select the donor, we look at the smallest d absolute differences, with d being equal to 5. Okay, that's what mice does by default when we use predictive mean matching on its default method. Predictive mean matching, it's also the default method in mice for continuous variables. Okay, and some of you that used mice in the assignment, so basically you didn't change the default, so we were not implementing the approach that we were required to implement in the assignment, because you need to change the default, the type from 1 to 0, and the number of donors from 5 to 1. Okay, and also we know that we have already talked, and it's kind of obvious that the risk of predictive mean matching is the duplication of the same donor many times, and this is more likely to occur if our sample is small, and also simultaneous if the proportion of missing data is large. And I finished this part about predictive mean matching quoting Van Buren, the author of the mice package and also of the book Flexible Multiple Imputation of Missing Data. And he basically says that this method, predictive mean matching, works best with large samples and provides imputation that possesses many characteristics of the complete data. Predictive mean matching cannot be used to extrapolate beyond the range of the data, obviously, right? Because then we are using the value of the donor, so we are limited to use the values that are observed in our sample. There is no way that we can come up with a value that was not observed. In some ways, it is good because we do not fall in the case where, for instance, we are imputing negative values for a variable that needs to be positive, but also it somehow weird that we cannot impute a value that was not observed in our data set. And it also says that it may not perform well with small data sets. And having these points in mind, predictive min matches is a great all-around method with good properties. Okay, and that's why he shows predictive min matching to be the default in mice. And so far we have discussed what mice does when we have one variable with missing values and that variable is continuous, right? Then once we have imputed, we go to step 2 and we use this function with, and here in with then we can use functions. For instance, if we are interested in a linear regression analysis in our analysis of interest or in a generalized linear model, then we can use our functions LM and GLM objects in our second step, and then the function pool, we put everything together, or function pool puts everything together for us, but we will be looking in the details in the next video. Now, just to conclude, uh, we have been talking about methods, normal linear regression methods or predictive min matching. That's the main idea behind is also fitting a normal linear regression model. So if our variable is not continuous, we might need different regression models. And the principles that we have outlined, so we fit our model of interest to the complete cases, and then or we impute the values or we take the value of the donor, these principles remain the same. But what is the default in mice? Well, if our variable to be imputed is binary, then using a logistic regression model, it seems a sensible approach, and that's the default in mice, and the method is logreg. If the variable has k categories, so not only like 0, 1, or 2 categories, but k unordered categories, then the default is polyreg. And if we have k categories but they are ordered, so mice does this by default. And just to outline the main principles, for instance, imagine that we have a binary random variable that can only take values 0 and 1, right? And I have some missing values and all the other variables are observed, right? So in this context, my y is binary, so it only takes values 0 and 1, and my x's, they are all observed, right? So I know that I'm just explaining what step 1 would look like. And again, Evil is in the details, and I'm just outlining the main idea. So if I have that yi, I will use logistic regression to impute my missing values. Okay, so yi, binary missing values, or as missing values, axis fully observed. I know that I'm using a logistic regression, so I'm saying that's my to the observed cases, right? So I know that they follow from y up 1 up to m. Okay, and I know that this is correct. And then based on my complete cases, on my observed, sorry, based on my observed cases, I estimate my regression coefficients, right? In mice, they also use a Bayesian procedure, so beta are draws from the posterior distribution of the parameters. I can also do this bootstrap version, okay? And once I have beta estimated from the observed data, what I do is I predict my so what I do is I can come up with my predicted probabilities, right? So can use, and I know that these predicted probabilities, right? Uh, they are between 0 and 1, and then I can generate, for instance, a uniform random number. And for instance, if the generated uniform random number falls below our predicted probability, then our will be 1, and otherwise it will be a 0. And this is one possible way to impute missing values when the variable with missing values is binary. So basically, to the complete cases, we fit a logistic regression model. We extract our regression coefficients, no matter how, bootstrap, Bayesian linear regression. So I can come up with the predicted probabilities for those with missing values. That's exactly what I have here. And I know that I want to impute a 0 or a 1, right? And I know that this is a value between 0 and 1, this predicted probability. So I can just easily generate a uniform random number. And if it falls below, it's a 1, and otherwise it's a 0, or the other way around. Okay. And this is just to give you an idea. And as I've said, then in the next video, we will be more practical and go to R and do this in practice. But I think that's a good idea to know, or to have a rough idea, even if we do not know all the details, then how exactly like the posterior distribution is calculated. And there are a lot of details that are out of our scope at this level. But I think we should have an idea of what the methods are doing, and not using it as a black box and without having any idea of what are at least the at a high level of what is going on. So I see you in the next video in R. Thank you.